Hello everyone and welcome to this lecture on partial differential equations. So, we will start with parabolic differential equations of the following form. So, this kind of equations are found a lot in engineering because heat transfer, transient heat transfer, this becomes the thermal conductivity. Similarly, for mass transfer this becomes the mass diffusivity and so on. So, it is important to first analyze this kind of equations. So, this equation is first order in time, but second order in space, and it is a parabolic differential equation. So, because it is first order in time, it requires one initial condition. And because it is second order in space, it requires two boundary conditions. For example, this, where I have said that the domain is between 0 and 1, x equal to 0 is the left boundary and x equal to 1 is the right boundary. So, these are two Dirichlet conditions for t greater than 0 at the boundaries, while this defines the initial condition. Okay. So, one can do something called as separation of variables. So, let us say the solution for u is of the form f of t multiplied by g of x. We can assume that the solution is in a separable form and it is given by this. Therefore, del u del t is simply df dt times g, and similarly del 2 u del x2 is simply f times d2g dx2, where we have written down explicitly that the partial differential equation is the partial derivatives are converted to ordinary derivatives, because g is only a function of x and f is only a function of time. With this consideration, we can write this, and therefore we can rearrange this slightly in the following form. So, we obtain this. This is only a function of time and this is only a function of x, and by virtue of this, each of them has to be equal to some constant which we call minus lambda square. The reason why I have chosen minus lambda square is because the solution for f in this present form will be some exponential of minus lambda square t. So, lambda square is always positive. The rationale behind writing it as minus lambda square is always positive, and hence this term is always negative. Okay. So, it will be e raised to minus some negative term times t. It is an exponential decaying solution. It cannot be an exponentially rising solution because it will blow up in time. In certain cases it may be, but in general it is exponentially decaying. So, 1 by f df dt is equal to minus lambda square, and d times 1 by g d2g dx2 equal to minus lambda square. Okay. So, the point over here is f is equal to e raised to minus lambda square times t, forget about the constant for now, and g equal to c1 sin lambda x plus c2 cos lambda x. We have already seen in the previous lecture that for such kind of equations, if the characteristic equation roots are negative, then we obtain this. In this I have explicitly removed d, because see, in the end consideration of d does not matter, because d is a positive quantity and we can always absorb d inside lambda square and we can have this. So, we have forgotten about d for now. If we did take, then lambda square would be simply lambda square by d, nothing else. We have written the simple thing. Okay, so now the solution is f times g. Okay, so let us say a is the constant. So f times g is equal to the solution u, which is equal to e raised to minus lambda square t a times c1 sin lambda x plus a times c2 cos lambda x, and this is equal to e raised to minus lambda square t p sin lambda x plus q cos lambda x. So here we have made no allure to what lambda is. Lambda could be anything, lambda is arbitrary, and hence the solution is valid for all lambdas. Hence the summation of this would give a more general solution. So u in general is this, but I do not know what lambda is. So lambda has to be fetched by means of the initial and the final the boundary conditions. So here look, p and q are the two unknowns in this equation, seemingly so, but lambda is also an unknown because we have introduced lambda over here without any additional constraints. So one of the initial or the boundary conditions will tell us what lambda will be. So lambda is found out as a part of the solution. The actual solution will then be u equal to summation of e raised to minus lambda square t p sin lambda x plus q cos lambda x, and then by various uses of orthogonality, this will be a part of the assignment, we can find out what the constraint on lambda will be and so on. Okay, especially for a finite domain, it will be a very good summation. Okay, but so is there any general solution available when the domains are not bounded? When the domains are bounded, we have the general solution, and by making use of the boundary conditions and the initial conditions, we can find out what lambda will be. But can we find a solution for x tending to infinity, essentially a semi-infinite wall? What is the solution for this? See, because t will go from 0 to infinity, we cannot take t from minus infinity, so t is semi-infinite, and let us say x also goes from minus infinity to plus infinity, or if x can go from 0 to infinity even. So x is unbounded, there is no sort of length to bound it. There is something called as a similarity solution, which is one of the most powerful ways to solve various kinds of partial differential equations which do not have any bounds, do not have any bounded length scales or time scales. And boundary layer theory, there is a very famous equation called the Blasius equation, which makes use of similarity solution. And one can have various kinds of problems in which there are thin films and so on, where the rupture of a film is also governed by a similarity variable. The reason why it is called similarity solution will be clear very soon. So for the same problem, let us say we have a solution V, which is some parameter raised to a times u. The time, let us say it is some s epsilon raised to b times t. Similarly, z is some parameter is equal to epsilon raised to c times x. So when we substitute this over here, what do we obtain? Substitution obtains, by substitution we obtain del t, so it will become del s. So t is s epsilon raised to minus b, and u is v epsilon raised to minus a is equal to, so let us say d is equal to 1 for simplicity. So x is z epsilon raised to minus c, and similarly u is v epsilon raised to minus a. We obtain this, and so we have del v by del s epsilon raised to b minus a is equal to del 2v del z2 epsilon raised to 2c minus a. Now, if the initial problem we have set d equal to 1, so the initial problem was del u del t equal to del 2u del x2, and by means of transformation we have arrived at an equation going from u as a function of x and t to a function v as a function of z and s, and we have this. But if these two equations are meant to be similar, then we should not have any dependence on epsilon, and therefore b minus a, if it becomes equal to 2c minus a, then we have so this if b minus a equal to 2c minus a. So essentially we have b equal to 2c. So this is the first constraint that we have on the parameters. So b equal to 2c. Now let us see, because we have 3 parameters, so we can club 2 of them at a time to have sort of only 2 variables in the fray, 2 sets of variables. Okay. So let us say we do the following transform: v by s raised to a by b. Okay. Then we obtain v is epsilon raised to a and s is epsilon raised to b times t, this raised to a by b. So this is epsilon raised to a u by epsilon raised to a t raised to a by b. This is equal to u by t raised to a by b. So it is clear that the combination v by s raised to a by b is invariant under this particular transform. Similarly, we have z by s raised to c by b is equal to epsilon raised to c x divided by epsilon raised to b times t raised to c by b is equal to epsilon raised to c into x by epsilon raised to c t raised to c by b, and this is as good as x by t raised to c by b. So under this transformation as well, this particular combination also remains invariant. Z by s raised to c by b is invariant as x by t raised to c by b. So then we have an equation which is invariant. We have an equation which is invariant and 2 particular combinations of variables which are also invariant, and so we can write down the solution u by t raised to a by b as some function of x by t raised to a by b, because we know that the equation is also unchanged and the boundary and the groups of the parameters are also unchanged. So we must have some kind of functional relationship between this and this. Okay. Essentially we must also have that the boundary conditions also remain invariant, and we will see that in case of problems dealing with infinite boundaries it is also the case. Okay. So we have found out this, but we already have b equal to 2c. This is c by b. Okay. So if b equal to 2c, this becomes function of x by, so c by b is equal to half, so this. Okay. So essentially we have u, the solution we have is u equal to t raised to a by b times f of x by square root of t. So now let us see if we let us see what del u del t is. So del u del t is a by b t raised to a by b minus 1 times f. So let us call eta equal to x by square root of time, so f of eta. So plus t raised to a by b. Now del f del eta is as good as df d eta times del eta del t. So, this is a by b t raised to a by b minus 1 f plus t raised to a by b df d eta multiplied by x by t raised to 3 by 2 times minus half, because we have taken a derivative of 1 by square root of time. So, this is as good as a by b t raised to a by b minus 1 times f plus t raised to a by b. So, we take 1 t over here and 1 square root of t. So, this becomes x by square root of t times df d eta times minus half, and this becomes t raised to a by b minus 1 common a by b times f plus, so this is t raised to a by b minus 1 that goes out, and this term is simply eta df d eta. This is the first term times minus half. Okay. And similarly, let us see what del u del x is. So, if we have the solution of this form, del u del x will not involve anything to do with this. We have simply df by d eta times 1 by square root of time. Del 2 u del x2 is then t raised to a by b d2f d eta 2 times 1 by t. So, this is t raised to a by b minus 1 d2f d eta 2. Okay, so if we combine this and this, what do we have? T raised to a by b minus 1 a by b f minus half eta df d eta is equal to t raised to a by b minus 1 d2f d eta 2. So, this t raised to a by b minus 1, t raised to a by b minus 1 we can remove from both the sides because it is not 0. So, this solution is uniformly valid for t greater than 0. Okay. So, we can remove that. So, essentially we have converted the PDE into an ordinary differential equation, and we can use all the machinery that we have learned for solving this kind of equations. But now let us see what about the boundary conditions. At t equal to 0, we have suppose u equal to 0 everywhere, and as x tends to infinity, we have say u equal to 0. So, this first initial condition represents where u is 0 everywhere in the domain. Second one says as we go very far from the wall, we have 0, and we can say that at for t greater than 0, u equal to 1 at x equal to 0, or u equal to u0, let us say. So, this is the left wall. Okay. So, the domain looks something like this. Here we have the value u equal to u0. Okay. So, then let us see what happens to the parameter eta. T equal to 0 means eta tends to infinity, and x tends to infinity also means eta tends to infinity, and for both of these we have u equal to 0. So, essentially what we have is t raised to a by b f infinity is equal to 0. This is the first condition. Okay. So, simply we mean, so t goes to infinity, right. So, a by b has to be less than 1 to be bounded, and it has to be positive for sure. Similarly, the second condition, for t greater than 0, u equal to u naught. So, what do we have? T raised to a by b f. Now, at x equal to 0, this eta parameter becomes 0. So, what is the meaning of this? The meaning of this is t raised to a by b has to be 1, which implies a by b has to be 0. So, substitute this over here, we can get rid of. So, this was the initial the conversion of the partial differential equation to the ordinary differential equation, and if we set a by b equal to 0, we have then the final form. Okay. So, this is the conversion of the transient one dimensional heat equation into an ordinary differential equation. So, this will find use in boundary layer theory. Okay. So, now that we have considered the two standard solutions of partial differential equations, we will briefly make an attempt to have an outline of perturbation methods, because oftentimes when we non-dimensionalize our governing equations, we end up with various groups of parameters which, depending on the kind of problem, may give some physical insight. Sometimes a parameter can be too small, sometimes it can be too large. In low Reynolds number hydrodynamics, the Reynolds number is too small. In case of boundary layer theory, the Reynolds number is high, and so these kinds of parametric the origins of these parameters give us more physical insight. So, the former gives rise to elliptic equations and the latter gives rise to parabolic equations. And so, let us have a look into a very simple equation. This, where epsilon is very small. Okay. And let us say we have some let us not call it y0 and y1, let us call it as simply a and b. So, this is the equation and epsilon is very small. So, we can use the characteristic equation m square minus m square plus 2 epsilon m minus 1 equal to 0, and we have m equal to minus 2 epsilon plus minus under root 4 epsilon square plus 4 by 2. So, m is minus epsilon plus minus square root of epsilon square plus 1. So, we have the two roots, and so the solution will be y equal to, so m1 comma 2, the positive root is m1 and the negative root is m2. C1 e raised to m1 x plus C2 e raised to m2 x. We can have a solution like this, which satisfies everything and everyone is happy. However, we can make use of the fact that epsilon being small is like a perturbation to this equation. Okay. So, we can make use of the smallness of the parameter epsilon, and let us say if epsilon were to identically be 0, then the governing equation was simply this. It is still a second order differential equation, and still we may have some boundary conditions which are close to the actual boundary conditions, but because of this perturbation may be different. But let us say we had some boundary conditions. And then the presence of this small term, because if dy dx is bounded and epsilon is small, this term is like a perturbation. So, whatever the solution is there for this will be perturbed by the presence of this term. So, let us say we have y is equal to y0, where y0 is the solution of this equation, but we can prove that in a more rigorous manner, plus epsilon y1 plus epsilon square y2 and so on. where y0 is known as the leading order solution, y1 is called as the first order perturbation, and so on. Okay. So, essentially we have said that the solution y is some base solution y plus the perturbation because of this term. If we substitute this in this, we obtain d2 y0 dx2 plus epsilon d2 y1 dx2 plus epsilon square d2 y2 dx2 and so on. The second term will be plus 2 epsilon dy0 dx plus 2 epsilon square dy1 dx plus order epsilon cube, and the third term will be minus y0 minus epsilon y1 minus epsilon square y2 and so on equal to 0. Okay. Now we collect various orders of epsilon. So, order 0, which is epsilon raised to 0, we only have these two terms, this and this. So, d2 y0 by dx2 minus y0 is equal to 0. Order epsilon. So, order epsilon, we have this term, and this term. Similarly, so essentially we have a cascading of terms where the leading order is the base equation where epsilon has been set to 0, that is like the 0th order equation, and then the solution of this aids to find out the first order term, which is y1, and y1 is actually the perturbation. So, the base solution contributes to the perturbation solution, which is order epsilon. Similarly, the first order solution y1 contributes to the solution y2 and so on. Okay. But now we must find out in similar cascading of the terms the boundary conditions for various terms. So, the boundary conditions that we had defined were y0 equal to a and say y1 equal to b. Now, y0 can be written as y0 plus epsilon y1 plus epsilon square y2 and so on at x equal to 0 equal to a, which implies if we match orders of epsilon, y0 is orders epsilon raised to 0 and a is order epsilon raised to 0, and hence the boundary condition for the 0th order term is simply y0 equal to a. Similarly, there is no term with epsilon or order epsilon square, and hence y1 will be 0, y2 will be 0 and so on at x equal to 0. It is only this non-zero solution y0 which will contribute to the governing equation, while all the boundaries will become 0. Similarly, y0 plus epsilon y1 plus epsilon square y2 at y x equal to 1 is equal to b. Okay. And if we compare the order epsilon raised to 0 term, we have y0 equal to b. Similarly, y1 at x equal to 1 and y2 at x equal to 1, they will all be also 0. So, all the governing equations apart from the order 1 equation, the 0th order equation will have a homogeneous boundary condition, that is y equal to 0 at both the ends except the 0th order equation, and this order equation will percolate, so to say, in the first order equation, and that solution will sort of percolate to this. So we have a cascading of terms which essentially gives us the final solution. So this is not to be confused with a Taylor series expansion. This is not a Taylor series expansion, but this is called as a asymptotic solution, and this particular case is called as a regular perturbation expansion. So if we have, say, a boundary like this, which is sort of at y equal to 0, but there is some function of x which is sort of perturbing. So in such kind of cases, it is not usually convenient to represent the boundary condition at the interface, because the interface may be unknown, and the interface may be sort of the unknown that we must find. So there is a small thing that I will show you here, and it is called as the Taylor series expansion. So y at f equal to x. So if some function f phi, let us say, so some function phi which is valid at y equal to fx. So phi at y equal to fx will be phi at y equal to 0 plus del phi del y times delta y, but now here locally delta y is as good as f of x. So this should be phi plus 1 by 2 factorial del 2 phi del y2 times f of x whole square, and so on. So essentially we can represent the value of phi at y equal to some function of x which is sort of oscillating around the value y equal to 0 as phi at fx equal to phi at y equal to 0, which is the flat surface, plus del phi del x at y equal to 0 times fx, and so on. The advantage of doing this is that we have converted a boundary condition on a curved boundary or on a non-uniform boundary onto a flat boundary plus its approximation, its gradient approximation on the flat boundary times the function, and thus the problem becomes much easier to solve, and this forms the basis of domain perturbation. Okay, this may be important in the chapters dealing with instability and so on. So by means of this we have covered similarity solution, we have covered the variable separable solution, and we have also covered how we can sort of do a Taylor series expansion to sort of modify a wavy boundary into a flat boundary while still having the information about the wavy boundary by a means of a simple Taylor series expansion. So we will proceed from here and let us see what goes on. Thank you.